In this video, we're going to provide you with a simple introduction to the logic gates for AND, OR and NOT. Now, it should be noted here, and this is important to understand, that nowhere in your specification does it actually require you to know about logic gates, logic gate symbols or circuit diagrams. So you're probably wondering why we're showing you this video. Well, what the spec does ask you to do is to understand how to apply the logical operators AND, OR and NOT in the context of truth tables. We're going to go over truth tables and scenarios with truth tables in the next two videos, but we really feel having a good understanding of the logic gates associated with them will make you a much better learner, and you'll be able to answer these questions more easily in the exam. So you don't need to take notes on this video, but please do watch it thoroughly first before watching the next two. By using binary digits, you can build electric circuits to process data. Circuits are built using components that carry out Boolean true or false operations. Here's an example of a circuit that can add binary numbers together. Now, this is more complex than the circuits you need to study at GCSE, but it illustrates their use. You will notice that the circuit is built using three types of components or Boolean operations. We sometimes call these gates or logic gates. There's a NOT gate. There's two examples of an AND gate. And there's an OR gate. Let's explore what happens to the signal entering and leaving each of these gates to better understand how they work. So first of all, the NOT gate. The NOT gate is very straightforward. We can either supply it with a naught, so you can think of that as meaning no current is supplied, or a 1, which means an electrical current is being supplied. The NOT gate simply reverses the input. So if a 0 is input, a 1 is output. If a 1 is input, a 0 is output. The second gate is an AND gate. Now this gate takes two inputs. Like the name of the gate suggests, both of these inputs need to be on. They need to have an electrical current. They need to have their inputs at 1 for the output to be 1. So if both inputs are 0, the output is 0. If only one input is a 1, so only one input has an electrical current, the output is still 0. Same if we swap the two inputs. It's only when both inputs receive a current, so they both have a 1, that the output is also 1. The final gate is an OR gate. Again, as the name suggests, we have two inputs, but either of the inputs can be on for the output to be on. They don't both have to be on. It's one or the other. So in this situation, where both inputs are 0, the output is 0. Now we have at least one input as a 1, the output is 1. The same if we switch them around, and indeed the same if they're both on. We have seen that we can combine these various logic gates to create logic diagrams, and this is something we're going to cover in more detail in another video later in this series.